We're going to learn about simulating physics by looking at the problem of a falling ball. So I have drawn a diagram here. This is a thing called a Freebody Diagram. It shows the forces which are acting upon the object and the coordinate system in which we will be doing our calculations. So there are two forces. There is gravity pulling downwards, and there is drag, which opposes velocity. So velocity will be downwards, this ball is falling, so drag will be upwards to oppose that. There is one parameter which we're calling h for height, and that is the height in meters of the ball above the ground. Now the equations that describe this system are given to us here. What we have is the acceleration is given by these relations here. Note that it depends upon velocity, that's the drag contribution. The velocity is being calculated using a form that looks like this. So let's actually talk a little bit about the structure of this equation. So on the left hand side we have velocity at t plus delta t. So the way that we understand this is we assume that we know the velocity at a time t, and what we want to do is calculate the velocity at some slightly later time, which will be t plus delta t. Delta t may be a small time step, a tenth of a second or a hundredth of a second or something like that. And so we calculate the velocity a little bit into the future by taking the current values and applying some update. So the current value is here, that's v of t, and the update is this one, the acceleration times delta t, the time step. Similarly, for the height of the ball a little bit into the future is predicted to be the current height plus some correction for the motion that has occurred during that time step. So that's the structure of these equations. So how would we actually implement this into MATLAB? Well, the first thing that we're going to need are the physical constants, and so these are given just below the equations there. We have the acceleration due to gravity, the drag, and the weight or the mass of the ball. Now that we have these constants, we can start storing these values. So I'm going to store the velocity as a vector. What I mean by that is every item in the vector will be the velocity at a new time step. So I might start with an array or vector that contains only a single value. This will be the initial velocity of the ball, and that's going to be 0. I say the ball is at the very beginning of our simulation, the ball is not moving. So it starts with a velocity of 0. And now what I'm going to do is update this velocity so that I know what it is at a future time step, a little bit into the future. So let me set up my delta t parameter, which I will choose to be a tenth of a second, a timescale which is fast relative to the physics of what I'm looking at. Now I need to know what is the acceleration. So the acceleration, I simply read off this equation times the current velocity. So I'm going to use the subscript 1 here to indicate that I want the velocity right now. Velocity squared minus g. And I am now in a position to write down what is the next velocity value. The next velocity value is the current one plus the acceleration times delta t. So if I run this now, let's have a look at the values in v. I have starting from 0 and then 0.1 of a second later, this is the velocity. It's negative because the ball is falling downwards. And so now I can do this step again. So I can take my acceleration and I will use now the second value in velocity. That's the most recent one. I will use the second value here to get a new acceleration value. I'll just overwrite the previous one. And then I will update. I'll get the third item in velocity, depends upon the second one plus that correction. And if I run that, let's have a look now. So now I have the velocity has increased. The ball has begun to fall a little bit faster. It's been accelerated by gravity. And so then I could do this again. And I can now say I want the fourth item. I can run that, have a look, and I see that the ball is still falling faster yet again. And so what's going on here in this code, let me put some comments in to make this a little bit clearer. So we have the physical constants, which are here. We have the initial conditions, which is that the velocity starts out at 0. And now what we're doing here is we're calculating for t is 1 times delta t, so 1 step of delta t, because this is the second value in our vector. Then here what's happening is we're calculating what it's like for 2 time steps into the future, and then 3 time steps here. So this would obviously get tedious very quickly if I had to copy and paste this for every single time step. I'm probably going to want hundreds of these. So what you're going to need to do is express this update in a loop. And you can see that there's a very repetitive pattern here. So this would quite easily translate into some sort of looping structure where you are updating, calculating the next velocity in the sequence according to these equations. Now you would also want to add in the position of the ball as well, and so we would treat that in a similar way. I use h for the position. Let's say it starts 5 meters above the ground. Well, then we were going to do an update. The height at the first time step, or the second time step I should say, the height at the second time step is the first time step plus the velocity times delta t. And so I will repeat this equation, just updating the values. Again, you would want to do this in a for loop in a realistic simulation, but I'll just put these numbers here to explain the concept. So let's have a look at that. And we can look now at the height of the ball, and we can see at the beginning we started at 5 meters, and then a little time later we have fallen to a height of 4.7 meters. And so in that way now we're able to track the motion of the ball. Now how would we know the actual time steps? Well, we've put them here in these comments. How can we generate that as a vector? What we can do, we know that time starts at 0. We know that it moves in steps of delta t, and we go up to, how many do we have here, is 3 times delta t is the upper limit. So here are the actual time values that correspond to each of these. So I will put h and t side by side so we can look at them. This means that at 0 seconds the height is 5. At 0.1 seconds the height is still 5, the ball's hardly moved. At 0.2, however, it started to accelerate, we get 4.9, and so on like this. So each time value here corresponds to a particular height in this vector here. So that's a basic approach for how we can simulate physical motion in a MATLAB script. So your task for this lab is basically to implement this with a looping structure and then to plot the results at the end.